Hello and welcome to a new installation in our BQIT lecture series. Today we'll be continuing our content on quantum algorithms. Today we'll be covering the quantum Fourier transform, and as a preliminary, we'll be also be going over the basics of discrete Fourier transforms, and we'll also be covering variational quantum algorithms. So to start with the discrete Fourier transform, the discrete Fourier transform is basically a mathematical tool that transforms discrete time signals into the frequency domain. So let's say we have this signal called x, and let's say it repeats and let's say we have this following signal right here. As you can see, this signal is constant, so it has no frequency. So in the frequency domain, we'll have a single peak at 0. And this value will be 5 because we have 5 entries over here. And then the rest of these entries will be 0. So the discrete Fourier transform basically tells us the different frequencies of the signals that make up the entire signal. And it is a fundamental routine in many algorithms that are used in various fields, such as signal analysis and image processing. So the mathematical definition of a discrete Fourier transform is as follows. We have two equations. The first is called the analysis equation, which is the direct, of course, the discrete Fourier transform. And the inverse of this transform, which transforms signals from the frequency domain back into the time domain, is called the synthesis equation, or the inverse discrete Fourier transform. And these are defined as follows, where capital N is the total number of data points, and N is the index of each data point, and K is basically the indicates the frequency. So that's, for example, if you have a signal n equals 4, for this case, taking the inverse Fourier transform would just give us 4 signals that are constant. And let's say we have a period of, we have this following signal, we get 4 points. And of course, the period of this point is 2, of the signal is 2. So from this mathematical definition, we can convert signals from the time domain to the frequency domain and vice versa quite easily. So to give you another example of deconstructing a signal from the time domain using the discrete Fourier transform, let's say we have this signal over here. So we have with an amplitude of 3, amplitude of 1. And if we take the discrete Fourier transform over here, we get this result over here. So from this, we can tell that this signal consists of 8 entries with frequency of 0 and 4 entries with frequency of 2. And this translates into the following decomposition. So we have this signal of 0, and then we have this signal which has a period of 2, and it goes from 1 to -1, and this is stuck at 1 basically. And so this value over here is actually the value of the Fourier transform at the frequency 0 divided by 4. And this is the value of the Fourier transform at the frequency of 2 divided by 4. And so this 4 value is sort of a normalization constant. So in addition to the discrete Fourier transform, we can calculate it using what's called the fast Fourier transform, which is basically an algorithm that allows for us to efficiently evaluate the direct Fourier transform of signals. So The fast Fourier transform is basically performed by matrix multiplication. So we would multiply a matrix to our signal to get the reconstructed discrete Fourier transform. And this takes n squared complex multiplications and n times n minus 1 complex additions. So it's on the scale of n squared in terms of space complexity. In addition, there's another method, it's called decimation in time fast Fourier transform, which instead performs the multiplication in certain stages, log 2 to the n stages. So in each stage, there's n over 2 different branches, and this gives us n complex multiplications and n complex additions. So we have a speed up from the simple version of matrix multiplication, which gives us a complexity of n to the log n. So moving on to the quantum Fourier transform. Quantum Fourier transform is basically the quantum analog of the discrete Fourier transform, where instead of a classical discrete signal, we have information that is coded in quantum states. So where we had this x of k is replaced by a y of k state, which would be inside a ket. And then this is transforming our original state over here. So it's transforming one wave function to another wave function in terms of a different basis. So mathematically, if you have this signal over here, represented as a column, we can deconstruct it linearly like so. Like so. So this is basically a review of the discrete Fourier transform. So according to this synthesis equation, we can write this as so. And so performing the direct Fourier transform gives us this signal right here, the discrete Fourier transform. So in a quantum case, instead of having these signals, we have these states, which also represent the frequency and the time domains. And as you can see, the definitions are almost identical, except we just replace these signals with states over here, so this is basically the definition of the quantum Fourier transform. So as we did above, we can also reconstruct states using the quantum Fourier transform in terms of the frequency domain or the time domain, and vice versa. So for example, for n equals 4, if we represent these four basis states as so, then applying the quantum Fourier transform to get kf in the frequency domain obtains this wave function over here, right here, as so. So in the frequency domain, we can rewrite these over here. And if you notice, these are actually the columns of the fast Fourier transform matrix. So we've covered the quantum Fourier transform's definition. We can also show that the quantum Fourier transform transforms states or states that are part of an orthonormal basis into other basis states. So orthonormality is actually preserved using the quantum Fourier transform, which makes it quite useful for obtaining a new basis in the frequency space. So this is the proof, beginning with the definition. we simply plug these numbers in here, and we get this form over here. We can take these sums together and rewrite it as so. And of course, this inner product is, of course, can be written in terms of the coordinate delta notation. And this is the final result we get over here. So there are two cases where k is equal to k prime. If k is equal to k prime, then this goes to 0. This exponent value goes to 1. And then we have n of these, so this value would still be 1. So, of course, it is normalized. If k is not equal to k prime, let's say k minus k prime is n, which is an integer, like so. And then we get this value over here, and then rewriting this using the formula for infinite geometric series, we can get this form over here. But this and this is equal to 1, which means that this term becomes 0. So this is also 0. So we get that in the case where it's not equal, the inner product is 0. So it indeed satisfies orthonormality. So we've covered the classical case and the quantum case of the Fourier transforms. And we've seen how they preserve the property of orthonormality. We can use this to, of course, to encode information into quantum states, periodic information into quantum states, and use the quantum Fourier transform to find information about its period in data. So, in order to do this, we need to create a circuit that implements the QFT. So, if you notice, let's say we have this state, general bit string state X, and then we try to perform the quantum Fourier transform over here. Then by definition, we of course get this final result, which is due to the following derivation. As you can see over here, the following derivation over here. And then we could rewrite this as so, since n, large n is 2 to small n. And then, of course, this is a bit string right here, and so is x. And so we can write this in terms of a sum over here. Yes. And then we could reconstruct this bit string in terms of its corresponding single bits. So y equals 0 or 1 over here. So that's how we've rewritten it so far. And it turns out you can rewrite this as the tensor product of these following states right here. And so we're going to exploit this fact to construct a circuit that implements the QFT. So notice that if we apply the Hadamard gate to a single bit string 0, 0, 1, we get this final result. And so we're going to exploit this as well as this result, which where you wrote K is simply a rotation matrix, like so, a phase rotation. And this is the controlled version of this right here. Yes, so what we're going to do is implement the circuit using these gates. So first we begin, and to remind ourselves, this is the final state we want to implement the QFT. We begin with a simple bit string vector over here. And then we apply H1 over here, and then we get this result over here. And this is identical. Then with psi 2, we apply this controlled unitary rotation, which rotates it by an extra angle over here, x2. And so we continue adding controlled rotations here to rotate this angle until the correct value of x is applied. And then we do the exact same thing for the x2 qubit, except we reduce the number of controlled rotation gates by 1. And this is because as we go down in the qubits, this power is reduced by 1. And so we have to reduce the number of control rotations. And afterwards, you'll notice that the order of the qubits in this case is reversed. So we add swap gates, which switch the order to obtain our final desired state. So what's the final complexity of this? So we need, this is the total number of Hadamard gates and controlled phase shift gates, which is n for the first qubit, n minus 1, and so on and so on. So we get this final sum of n squared, but n is the log of n, so we get the time complexity of log n squared, which you notice is better than our best classical algorithm for the discrete Fourier transform. So the quantum Fourier transform does offer a speed up over the classical discrete Fourier transform. So let's move on to variational quantum algorithms. Now, a variational quantum algorithm is what's called a hybrid quantum classical algorithm, in which we combine classical methods of machine learning and optimization with our quantum to optimize our quantum circuit parameters in order to converge to the correct answer of the problem we're solving. So this is useful for noisy intermediate scale quantum computers, or NISQ, where there's a lot of errors. And so we use this classical routine, which is not affected by quantum errors, to inform our quantum algorithm. And it's called a variational quantum algorithm due to the variational theorem in quantum mechanics. So the variational theorem basically states for any Hamiltonian, the expectation value must be greater or equal to the final ground state energy. So if we didn't know the actual ground state wave function, we could just set up this guess or ansatz. And if we calculated the energy, assuming this ansatz was correct, it would be greater or equal to this ground state energy. So since we know that it is greater or equal to the ground state energy, we simply adjust our wave function such that its expectational value is at its lowest. And since we know it's never going to go below the ground state, we can just keep doing that and assume that the lowest value is the closest to the optimal value. So such variational quantum algorithms has various different applications such as quantum machine learning and solving classical problems such as the max cut problem, etc., etc. So one component in variational quantum algorithms are what's called reference states. These are the initial state of our problem that we begin with. So for example, some unitary R reference to the all zero state. And these reference states are used mostly to encode data. So to train classical data using a quantum computer, the classical data must be first embedded into quantum states, and these are embedded into these reference states. So there are many different methods of embedding such classical data into quantum states. One method is called basis encoding, in which we encode the different bit strings into the basis vector itself. There's angle encoding, in which each bit string is represented as an angle over here. Each piece of information is represented as an angle of the rotation. Of course, there's QAM encoding, in which we represent the final data as a superposition of different basis states that each represent a a bit of the classical data we're trying to encode. There's QRAM encoding, in which is similar to QAM coding, except it uses an ancillary system, which basically labels the number of the bit. And there's also amplitude encoding, which encodes the information in the amplitude of the different basis states. So moving on to the ansatz and the cost function. So the basic objective of all variational quantum algorithms is to minimize this expectation value with an ansatz that depends on some parameter theta. So this is called what's called the cost function over here, which is the expectation of the Hamiltonian. And the ansatz is basically the final state of our circuit. And some of the gates depend on the parameter values of the parameter theta. So our goal is to vary theta until we reach the minimum value of our cost function. However, one caveat is that since the dimensionality of the state space or the Hilbert space of n qubits is 2 to the n, sometimes referred to the recursive dimensionality, we need to impose some reasonable constraints on the variational form, such that only the most relevant states are explored. Otherwise, the exponential scale of the Hilbert space means that some states, most of the states there aren't relevant and irrelevant to our problem. So exploring the different combinations needed for theta might be challenging if this isn't imposed, if without these constraints. So when designing such variational quantum algorithms, there's a slight trade-off between search space, speed, accuracy, circuit depth, and noise. So if you reduce the search space, of course the speed is going to go up, but the accuracy may be reduced. And this also reduces the circuit depth and the noise, and vice versa. So for example, let's say we have this ansatz consisting of lots of different rotation gates, and for the parameters, the rotation angles can be set as the parameter. So the final component is how do we optimize our parameters to reach the minimum value of the cost function? And this is where the classical part comes in. Normally, we use what's called a gradient-based optimizer, which is basically defined by this formula over here. So we're measuring how much the cost function changes as we vary a theta, and we basically update the current parameter in the direction of the greatest change. But however, this runs into problem of barren plateaus, which is basically a flat region of the cost function, which makes it challenging to determine the appropriate direction to search, because if that region is flat, then this gradient is small, which means that it's difficult to determine the final optimal value of the next step. So to summarize variational quantum algorithms, first encode classical data using a reference state, and then it runs it through a variational quantum circuit, which is based on some parameters. And then the expectation value is defined as the cost function. And by using an optimization routine, such as a gradient-based optimizer, we update the parameters to get a lower version, a lower value of the cost function. And then we repeat this until we meet the minimum value of the cost function. And if we reach the minimum value, we conclude that that is in fact the answer to this problem. Now, of course, this involves a lot of tweaking to get the right ansatz, but generally the variational quantum algorithm is one of the first algorithms that is demonstrated to have some sort of utility on the current noisy quantum computers of today. So that's all for today's lecture. I'll see you next time.